This video will continue on simplifying radicals. Okay, so if we take a look at number 7, we have the fourth root of 80. So if we're simplifying this, we cannot use this list of perfect squares because the index is 2. We can't use this list that we created in a previous video because this is all cubes. So if we wanted to simplify this using method 1, we would have to make a list of fourth roots, perfect fourth roots. So we would have 2 times 2 times 2 times 2 is 16. And then we'd have 3 times 3 times 3 times 3, that's 81, etc. So since 16 goes into 80, we can write it as 16, fourth root of 16 times the fourth root of 5. And then what times itself 4 times is 16. The answer to that is 2. And then this can't be simplified any further. Now, personally, when this index is high, or if I have to really think hard about what perfect fourth root to use, I probably wouldn't, this would be one that I wouldn't use method 1, and I would have just made a quick factor tree using any two numbers I want that multiply to 80. And then I make my radical jail. The index is 4, so I'm looking for numbers that are the same. So there are 4 2's here. So only 1 makes it out, and then we have the 5 left. Okay, now as for the variables, we would just divide. 4 goes into 7 one time. So that is why we would have just an A on the outside. And then we would have 3 left. So we would have we would have A cubed in the inside. And then 4 goes into 8 exactly twice. So we would have no B's in the inside of the radical. And we'd have 2 out here. So this would be our final answer. Okay, let's go ahead and take a look at example 8. So we have the cube root of 56. So if we're using method 1, we could use our list of perfect cubes, and we have to figure out which of these go into 56. So 8 goes into 56. So we could use this one. So we would have the cube root of 8 times the cube root of 7. And what times itself 3 times is 8? The answer to that is 2, so it's no longer, the radical is no longer needed. Now we can also get that same answer if we just make a factor tree. We could use 8 times 7 still. And then because the index is a 3, we're looking for a group of 3. But only 1 makes it out of the radical, and then we have the 7. So same thing. Then as far as the variable goes, we divide. So 3 goes into 11 3 times. So we would have x cubed, and then the remainder is what would be in the inside. And now we would do the y's. And 3 goes into 3 once. So we would just have a y on the outside, and then there would be nothing left inside. So this would be our final answer. Okay, let's take a look at number 9. So again, notice in this problem here, we have a -5 already there that needs to be multiplied. So I want to make sure that I don't forget that -5 has to be multiplied to whatever answer we have outside the radical. So with method 1, we're going to use our perfect square list because the index is 2. And we pick which number on our list goes into 32. So 4 does, as well as 16. So I'm going to go ahead and pick 16. square root of 16 is 4. But then we already had the negative 5 in the front, so that's where we would get negative 20 rad 2. Now remember, if ever you want to check your answers, you could go back to the original problem, which was negative 5 times the square root of 32. And then jot down what the decimal answer is. It's about negative 28.28. And then take your answer. So for those of you who are worried about catching mistakes or forgetting to bring down the negative 5, if you're determined, always check by plugging in your answer in the calculator and then checking what you get when you plug the original problem in, and it should come out to be the same decimal. So that's a nice way to check your answer. Alrighty, last one here. So again, let's go over the visual way to do this. There would be 14 W's, and since the index is 5, we are looking for groups of 5. But there's not enough to make another group. So that's why we would have, there's 2 groups, so we would have W squared on the outside, and then we'd have 4 left in the inside. Okay, now we would do that for the X's. And we're looking for groups of 5. We'd only have 1 group, and we'd have 3 left. So again, this is essentially the same thing you would get if you would just use division. And then for the Y's, we have 10. And we're looking for groups of 5, because that's what the index is. And we'd have none left. They made even groups of 5, and there's 2 groups. So again, this is the same thing you would get if you just divide the index into the exponent.